All right, hopefully my screen is sharing properly. Yeah, that looks good. Okay. So, like I said, we're going to start off the second session by dealing with the second half of questions in last term's exam, which were the calculus. It was the calculus half of the exam, essentially. And we're starting things off with a pretty common kind of question, which is something that's asked us to integrate something, right? So in particular, we're being told how to integrate it even, which is quite convenient. And in particular, we're being asked to solve this integration by substitution. So we've been told we're going to make a substitution, plug it in somehow into our integral, and get an answer out, hopefully. And even more conveniently, I think for this sort of question, we've been told to sort of solve this in parts. So, I mean, certainly in the course notes, etc., you may have seen a question that just looks like this only, right, with no parts leading you through exactly what happens in each step. If you're given multiple steps to solve a problem, that's usually a good sign, right? It doesn't like don't be scared that there are multiple parts to a problem. It probably means that they're helping you along the way in some way. And in this case, it would also mean that if you made a mistake somewhere near the end in finding your final value, you could still earn part marks for getting halfway there. So that said, let's work through each of these parts in turn and see what happens. So for this first part here, part A, we of course know that we want to make the substitution. So first things first, we're going to, so I'll write it over here as well. Our substitution is u, is u equals 1 plus 1 9 x squared. And I need to, the first thing I want to do is find du in terms of dx. So of course, this is, you just want to differentiate. I like to be as careful as possible when I'm doing these sorts of things. I always prefer to write powers of x like this, so that I don't have to worry about getting signs wrong or anything like that when I'm differentiating. So that now I find du dx. And by looking at this thing on the right here, I can quickly see it's just going to be 0 plus minus 2 ninths of x to the minus times x to the minus 3. Okay, and if I want, I can clean that up a little bit. So it'll just be minus 2 on 9x cubed. But that's all I need to do there for this part, right? They want me to write du equals f, like equals something times dx, right? So okay, if I really wanted, I could write this at like this, but I think I can already see what my f of x is, right? It's this part here. So that would be my answer to part A. Maybe I'll color code them. So part A will be this function of x, so minus 2 on 9 x cubed. Okay, so, and of course I know that I need this to actually perform my integral by substitution in the end, so it will be useful to remember what I've done there. But now we can move on to part B. So in part B, we want to actually make the substitution, and this is often, well, I don't know, I'm sure people have different opinions about what's hard and easy in these sorts of questions, but usually if it's going to be something that trips you up, it might be this part here where you're rewriting the integral in x in terms of u instead. And typically, by the way, when we do integration by using a substitution trick, it's because we can see, or at least when I want to, I know that I want to apply it when I can sort of see somehow that there is some function u, and I can sort of spot somewhere hidden in the integrand as well, du dx, right? So essentially I can see u and its derivative sort of multiplied within, and then some constant fudge factor perhaps within the integrand. In this particular case, I don't think I would have guessed off the bat to make the substitution, right? to let u be 1 plus 1 on 9x squared, because I don't immediately see that in the integrand, and I don't really see the derivative minus 2 on x cubed in there either. So you know, so it's convenient the question actually told me what substitution to make, but it also means that it might be a little, there might be a little bit of work involved in actually making this step where I rewrite the integrand in terms of u. But that said, we have our du, and we know what u should be, so we can try to rearrange this expression to see what comes out. So if I just write the integrand, which is perhaps a bit, it's not great to write du's and dx's by themselves out of context, right? But I mean, this is just my sketching, like my working on the back of an envelope anyway, so I'm not too worried about rigor here. So what can I do here? There are a couple of options. I could just try to pull like u out of this expression somehow before I do anything, but it's probably more straightforward to just do a blunt force substitution. So I know what dx is in terms of du and x, which is also not typically a great thing to write, but as in mixing pronumerals. But it's a valid technique, and I think it might help in this case. So I'm going to replace dx with minus 9 on 2 x cubed du. And of course, I'm going to hope that that x cubed goes away at some point, because I need an expression only in u. And then on the bottom, I still just have x plus 9x squared, of course. Okay, so like I said, I'd prefer for there not to be an x cubed up in that numerator. So I think the next logical thing to do might be to just divide top and bottom by x cubed, which will leave me with, well, I'll pull the minus 9 on 2 out the front. And then it will leave me with the du up the top. Whoops, and on the bottom, I'll have 1 on x squared plus 9, 1 on x cubed. Oh no, sorry, 1 on x squared plus, oh, I see. Sorry. Always make sure you don't make typos when you're making these transcriptions. So I should have written x plus 9x cubed on the bottom now, which is why I'm left with 1 on x squared plus 9 on the bottom after dividing top and bottom by x cubed. Okay, so I'm hopefully almost there. I've only left with one x term now in this expression. How am I going to resolve it? Well, remember, I'm also looking to put u into this expression somehow. So I should remember that u is 1 plus 1 on 9. 1 plus 1 ninth x to the minus 2, or 1 plus 1 on 9x squared. And this almost looks like this, right? How can I get it to look exactly like that? Well, I could divide the denominator further by just 9. If I divide it through by 9, I'll have u on the bottom there. And to make sure I'm not changing the integrand, I would just divide the numerator by 9 as well, essentially. So that means my multiplier at the front would just become minus 1/2. And then maybe I'll do it in multiple steps. So then my denominator is going to become 1 on 9x squared plus 1, which is certainly what u is, right? The substitution we originally made up here, or wanted to make. So this is minus 1/2 du on u. Okay. And now I'm done, right? No more x's. I have expression only in u and du. And so what am I going to write for my answer in part B? Well, again, I only want to write the integrand. So the expression in u, not times du. So actually, let me write that even more clearly. So if I write it like this, then I can see that my function g of u will be this expression here. So minus 1/2 times 1 on u, or if you like, minus 1 on 2u. That would be what I would want to write for g of u, that is, for part B. Okay, so now I've done the two important steps, right? I've worked out what du should be in terms of x. I've worked out what the integrand should be in terms of u. All that's left to do is integrate. So maybe I'll do that over here. So what is this integral going to be? So I'm taking the integral of dx on x plus 9x cubed. Of course, I want to make my substitution. So this is going to be really the integral of minus 1/2 du on u. And we hopefully all know what that is. That's just minus 1/2 times the natural log of the absolute value of u, right? Plus c, but actually in this question, we've been told not to include the plus c when we actually write out our answer. Okay, and so am I done here? Well, not quite. We always should remember when we're making substitution tricks to ensure that our answer is actually in terms of the original variable. So if the integral is in terms of x, I better give an answer in terms of x, right? Not in terms of u. And the question reminds me of that as well, right? It says find the integral in terms of x. Yeah. So, well, that's simple enough. I could just make my substitution. We already said that u is 1 plus 1 on 9x squared. So really this is minus 1/2 log of this, 1 plus 1 on 9x squared. Okay. Now, it's not necessary for this question, but I could also have noticed at this point that the expression inside the absolute value sign, so 1 plus 1 on 9x squared, will never be non-zero. Sorry, will never be non-positive, right? So it's not a necessary step for this question, but I could actually remove the absolute value signs because a square term, so x squared is always positive, is always non-negative rather. For this to be defined, it has to be always positive, and therefore the whole expression will always be positive. So I don't need to worry about it ever being negative and the absolute value sign is actually changing the expression inside. Okay, cool. And so I'm done again, right? I've got my answer in terms of x. So this is what, but I'm ignoring the plus c as I've been told, right? I omit the plus c, very important. Otherwise the auto marker won't recognize my answer as correct, I think. So that blue box, or this blue box really, either of those should work as my solution. Okay, so the other thing we can do here, of course, is actually demonstrate how we would type these things in. So what did I say f of x would be? That would be the thing that I've boxed in yellow here. So it should be minus 2 divided by 9x cubed. Now, I should go back and check that what I've typed makes sense, right? Does this is what I've typed actually what I want to have written? Well, I can check with the preview button if I'm not sure. I'm actually told that there's a Maple syntax error at this point, so that's not a good sign. What could I have missed here? Well, I need to remember that when I'm multiplying any two things in Maple, I should always make sure I'm sticking in an asterisk. Okay, does this look like it will work now? Well, I might just check with my preview again. And what do you know? It's not quite, right? I wanted minus 2 over 9x cubed. I've got minus 2 over 9 times x cubed. So also always watch out for your brackets. So here I would want to bracket the terms that are the denominator, right? And in fact, if I'm trying to be especially careful, I'll always, like if I'm ever writing a fraction, I'll always do this before I enter my numerator and my denominator, because then I'll be sure that they're paired off with brackets. And I'll check with my preview again. So yeah, now that looks like what I wanted it to look like. If you prefer, I tend to do this because I'm lazy, but I don't recommend it because it can make it a little less clear. But you might also prefer to write it as, well, it's minus 2 divided by 9 and also divided by x cubed or something like that, which should also give you the expression you wanted. Okay. Oh, and I guess also, if I wanted, I could say it's minus 2/9 times x to the minus 3. So I think that should also work. Okay. How about for part B?
Can we zoom in a little
yeah.
bit?
Oh, sorry. Yeah, I always forget that.
I was able to read it up to a certain point when the quality dropped.
Oh, sorry. And there's a question. Yeah, good question. So I'll get to that in just a second. So for for part B, same situation. I want to write minus half times. So I could write minus half times 1 on u. That should work, right? Or I could say on minus 1 over 2 times u or whatever. And then I'll just make sure that the expression is what I wanted it to be. And then, yeah, so finally for this integral, right? So okay, so I'll type in the thing at the bottom, like the final form we found first. So that would be minus 1/2 times natural log, which is just ln, of 1 plus 1 on 9x squared. Yeah, like that. I'll check with my preview button. Does that look like what I wanted? Yes, it does. So because we already established that thing in the absolute value is always positive, it should, and it does turn out to be marked as correct. But I said you didn't need to check that for this particular question because it was sort of the end of the question when you weren't going to manipulate that thing any further anyway. So we could have stopped here at the absolute value expression. So to answer the question in chat, what if I had included the absolute value, so the log of the absolute value of that expression? It should look something like this. So that it doesn't render the absolute value symbols, but we remember that ABS, or hopefully we've encountered ABS as the maple syntax for absolute value. So if I write that, it will, or it should, I think, yeah, also be marked as correct because it is evaluating to be the same thing at all valid points. Yeah.
I should point this previewer is actually something I wrote. I will try and fix that before the exam happens.
Yeah, okay, sure. Yeah, it's very convenient. Yeah, I think as much. Oh, the only thing.
Default one.
Yeah, right.
The only thing it does, which I like, is it will give you a few syntax advices, which you don't get from Maple by default.
Okay. Yeah, yeah. Well, yeah. I mean, of course, the more convenient it is, the better. But at the same time, Maple is part of the course, so and you like if you want it, you're allowed to have access to Maple for this open book exam. So you can also always check in there, I guess. But our intention is not to confuse you or trick you with notation errors, right? I'll just quickly point out here, down the bottom it says always use fractions, not decimals. We mentioned that before, but I'll just point out here, had I been lazy or whatever and written 0.5 instead of 1/2 in my expression, I believe the answer checker, the answer checker wouldn't have recognized that as correct, which is something I assume has to do with floating point calculations. So the fact that even though 1/2 is a finite decimal in decimal notation, in binary notation, it goes on forever. And so if Maple or whatever is checking answers against that, it's going to have to approximate at some point, which is not what we would like. So I think this is a nice demonstration of the fact that whenever you can, you should go for fractional representation over decimal. Okay, and then Henry's just saying, I wanted to check about the calculation for G of U, so for part B, I guess. So yeah, it's very much an algebraic manipulation step, right? I knew that I wanted this expression to be in terms of U, and I knew that I would have to use both these substitutions at least once each to get there. So because I need to get rid of the dx and I need to get rid of the x's, of course. Well, first of all, in this first step, we calculated du dx to get du in terms of dx, but of course, this also gives me dx in terms of du, right? If I just rearrange a bit. So this is, yeah. So these mean the same thing, right? If I just take the multiplying factor, invert it, and put it on the other side. So actually, I use this substitution in this first step. I replaced dx with the expression on the right. And that was just to introduce my du, because now I've dealt with the dx. And so that means any further substitutions I'm going to be making will be of this form. I'll be replacing terms in x with terms in u. And so from this step here, it's just like from this point, it really is just an algebraic manipulation exercise. So I need to get what's left in terms of x into something that looks like my goal. So that is this thing here, 1 plus 1 all over, or 1 plus 1 on 9x squared. And so first, I didn't want to deal with both numerator and denominator. X is in both of those, so I just divided the top through by x cubed, which meant I had to divide the bottom through by x cubed as well. So that left me with just this one term down the bottom, 1 on x squared plus 9 to worry about. And at this point, I could kind of tell by observation, I guess, just on sight, that it looked quite similar to the expression u that I wanted, right? If I wanted to make that super clear, maybe I could say, oh, hey, this denominator, it's actually 9 times 1 plus 1 on 9x squared. And that the thing in brackets, of course, being the substitution I want to make for u, right? And then the 9s are going to cancel, essentially. Or if you prefer, the way I said originally is I just divided top and bottom by 9, where I'm thinking of this multiplier, minus 9 on 2, as still being part of the numerator, I guess. I'm trying to think if there's another way to approach it. I guess you could try to make the du substitution right at the end, but it's a bit, well, I guess in the end you're sort of doing the same thing in reverse. But yeah, that's right, Henry. So you can manipulate, yeah, you can manipulate the u function to derive an x function in terms of u. Yeah, I guess that's essentially what we're doing. And yeah, Hugh's got a point that with experience or with enough intuition, you can kind of be thinking about, you can kind of be guessing what expression you're looking for. So I didn't really think I was going to have like a polynomial in u, just from looking at the expression I was starting with. And in fact, I was expecting something like 1 on u because, well, I guess the other thing you might have noticed here is that u is 9x squared plus 1 on 9x squared, right? And that already looks quite similar to this expression, just upside down, right? And like with some factor of x accounted for. So that makes me also think of the inverse of u as being important in some sense. And in fact, I think, yeah, if you felt particularly inclined, you could probably derive the expression we're looking for, so this one, from expanding out u like that, because I can kind of see, oh, okay, so 1 on u is 9x squared on 1 plus 9x squared. So if I multiply top and bottom by x, I'll have something that is very close to my expression. And there'll be an x cubed factor that I have to worry about. But what do you know? There's an x cubed factor accounted for in my du dx calculation. Yeah. So as is often the case, there's more than one way to actually get around these sorts of manipulations. In the end, you'll be doing variations on the same thing, but you might prefer a slightly different approach. My approach is sort of it's a bit I like to work through it this way because I know that I'm getting closer to the answer each step. Like I replace my dx with something in terms of du, so I never have to worry about dx's again. Then I simplified the numerator, so I only had to worry about the denominator. And then it was sort of a notice u by observation, or something like that. Arguably, this trick is the one you have to think most carefully about. But everything else is sort of automatic for me in terms of, well, what do I want to simplify next, kind of thing. Okay, I think that's probably all there is to say about this question. Yeah, you might have, you might have first looked at this and thought, oh, this kind of looks like 1 on 1 plus 9x squared, and start thinking about inverse tan. But yeah, it turns out it's a very different function, as we've learned, right? Based on the fact that the integral was in terms of log of some expression in inverse x squared, not anything to do with arctan, right? I guess I could also say, if you've encountered it in some other course, this type of expression, so finding this sort of integral, the first thing I think of really is using partial fractions to solve this. We didn't cover that in this course. You'll see it in MATH1231 calculus, Math 1b. But yeah, if for some reason you did happen to know about that approach, that's the one I would first take with this sort of integral. Even if you didn't know that sort of approach, you wouldn't use it here, right? Because the question is specifically set up so that you have to solve it using substitution. So it wouldn't help you in that case. But if I encountered this integral in the wild, the first thing I would try is using the method of partial fractions, which if you've heard of, you can attempt to use here. And if you haven't, well, you can learn about it next term, perhaps. Oh, Hugh, yeah, it might.
Actually, it looks like. I was actually looking at the responses for this one as well. A lot of people seem to have used partial fractions, or at least some of them.
Okay.
But they didn't help them with the first two parts, but for the last part, it came to the integral. So both of them are marked as correct. It marks any correct answer as correct, as it should.
Right, yeah. Because, yeah, I think you often, with these answers that involve log, you might get an answer that, if you use a different approach, you might get plus some constant fudge factor, like plus log 9 or something, I don't know, right? It would just be absorbed into the constant. So you would still end up with the same answer, it just might look different. And like in this case,
people are ending up with the inverse hyperbolic tan.
Oh, right, I see.
It does involve logs. If you remember the last lecture we had, you can solve the inverse hyperbolic tan in terms of logs.
Yeah, true. Yeah, that would be, I imagine, tricky to
not the same. It just
derive without. Yeah, that's interesting. But yeah,
so we should probably move on to the next question.
Yeah, exactly. Yeah. Yeah, G, it would be correct, even if you didn't use the absolute values, because in this case, the expression inside the absolute values is always positive. You can always play it safe and use the absolute value, because it'll also be marked as correct, and you'll never be wrong if you leave the absolute value symbols in there. Whereas if you choose to omit them, there's a danger that you let through a negative answer that shouldn't have been allowed.
All right, so I'll do the next question. Now, this question is actually surprisingly short. So let's just take a look at the question. So it gives us an improper integral. Now, there are no real tricks with this integral. It starts at a very high number, but really it's just because when I look at it, this number is actually 3 to the power of 7 plus 1. So the 7th root of this will be greater than 3. So this number will be positive. It's a strictly non-negative number. Sorry, it's a strictly positive number on the bottom for this. So there's no problem there. So you don't need to spot that. We're not trying to trick you. We're just trying to make it easy for you. Maybe a bigger number would be nicer, but anyway. Now, it tells us we're going to look at this question, and we're going to use the comparison test to decide whether it's a convergent or divergent integral. Now, for this, you really want to look at the improper integral and say, well, what's the behavior like? Which option should I be choosing? So I'm looking at this. Well, cosine doesn't really help very much. Cosine, it just oscillates between -1 and 1. So this thing at the top oscillates between 1 and 4. No, sorry, 2 and 4. So that's not really going to do much for the integral. And this thing tends to infinity, but it tends to infinity pretty much like x to the power of 1/7. So I'm thinking of an integral, some constant over x to the power 1/7 dx. So when I see this, this is my thought. It should look like this. So when I'm looking at the options, well, I guess first thing you have to ask yourself is, what type of integral is this? Is this convergent, divergent? How do we know? I am asking. Yeah, it's a P integral. So P integral with P, let's see, strictly less than 1, or less than or equal to 1, that's always divergent. So it's going to be divergent, so we need to prove it diverges. Now we need to think about what that actually means. Now it says I want to do a comparison. If it's divergent, what I really want is I want a lower bound which I understand the behavior of. So I really want this thing to be bigger than something I understand. So here it's saying smaller than, smaller than. These are not the options. It's one of these two. Now what do I want? So I want to prove that it diverges. I know it diverges, so I'm going to go for this one. So my choice would be the first one. Now, what we want to do is actually find a suitable choice. We'll need to do some thinking for that. So let's try just copying out what I think. So just this thing between 4 and 2, I want to find a lower bound. So I want to pick this. The thing on the bottom, x to the 1/7 minus 1, that's less than x to the 1/7, and it's positive for the region I'm talking about, strictly positive. So what does that mean for the reciprocal? So if I take the multiplicative inverse of these things, this thing will be larger. So that's great. This is a lower bound. So overall, I can say that a suitable gx, a suitable lower bound, would be 2 over x, the square root of x, so x to the 1/2. And that's all I need. So let's try that out. Not it. Where is my, yeah. No, that's Sean's question. Why are we choosing 1/2? I think I probably made a mistake if I said 1/2. So let's answer the first part. I want to choose this, a lower bound. And P, so sorry, A was 2, I believe, and P was 1/7. So what did I say, 1/2? Oh yeah, for some reason, I don't know, I'm so used to thinking about square roots. I lost the power. So that is less than that, is what I said. So this will be larger than that. So I want to pick this to the 1/7. Yeah, just a mental transcription error. So the power is 1/7 and x a is 2. How did I do? Good. Now, out of curiosity, did I have to be so exact? Because it's also true that this is greater than 1, for example. This is true. Was I smart enough to code this up? Yeah, so apparently it does work. It should not work for 3? No, it does not. So it does accept more valid answers, but this is the answer I got through my work. And that's really, I guess, all I need to say about this question. Do you have any comments, Sean, or any questions? Could I put in -20? Interesting. Maybe put your hand up if you think -20 should work. So no one's putting their hand up? No. And yeah, you have to look at the original question. I'll actually do it in the OneNote. Our original claim is we're going to give a g which is positive. A lot of the theorems in this course, when you're doing integration, rely on you having positive functions. So if I put in -20, let's just try it. It shouldn't work. No, it doesn't work. I'd be curious to know if there are more answers than just this, because there should be, but I'm not entirely sure how smart the system is. But yeah, this is the obvious answer. I'd put this in. 0. I mean, it is true that this is less than that. So it is true that this is less than that. This should come up wrong. It is wrong. I mean, it's wrong because this, if I integrate 0, I get a convergent integral. So I'm just proving that this thing I'm looking at is bigger than 0. I really want to show that it tends to, it like grows to infinity, this integral. So this doesn't give me anything useful. But I think any non-zero number, anything between 0 and 2 should be accepted, I believe. So the one that I think is obvious is 2, use 2. Why do we choose A rather than D? I mean, it's because it doesn't prove anything. So the trouble is, let's say I have the following. So I have an integral. I have an integral of some function I want to understand from whatever number to infinity. And I say it's less than this integral, sort of abusing notation. Let's say I say it's less than this. So what I'm writing is that the integral I'm trying to study is less than infinity. That doesn't tell me anything. There's sort of room for this to go anywhere at all. So this doesn't help at all. So I might actually write it that way. Let's say that is less than that. Yeah. Anyway, it's not the right behavior you should be looking for. If you're looking for divergence, what you're looking for is the lower bound. You're looking for something to push it off to infinity. So actually, I guess my initial guess was slightly wrong. When I was looking at this, I know it diverges. So I should have said not this, maybe this, but this is the wrong way around. So also not that. Yeah, if we were trying to prove it convergent, then we take this. I want to find something bigger which holds it down. Do you have any comments, Sean?
No, I don't think so. I think you covered all bases.
Mm-hmm.
So yeah, I guess maybe we'll move on to the next question then. Okay, so on to question 11. This is another one with parts that certainly lead you towards the intended answer. So our first, so we have two parts here. Maybe I'll do my color coding again. So for part A, what we want to do is find the derivative with respect to x of this function. In this case, I got cos of x times sine of x. So we're looking for ddx of this expression here. And so, of course, I've got two functions of x. I've got the product of two functions of x. So I'm going to be using my product rule, right? So that means differentiate one and leave the other, and then add to that what happens when you leave one and differentiate the other, if that makes sense. I mean, I would probably never actually write out the intermediary steps here, but just to make it super clear what's going on. I'm finding this expression here, right? Maybe I'll write like that. Okay, so really all I need to remember here is how do I actually differentiate my trig functions and my hyperbolic trig functions, right? So I remember by whatever mnemonic I've decided on that ddx of cos x is minus, it looks a bit like I've written cos of minus x, is minus sine of x, right? That's sort of the way I remember it, I guess, is it's the one out of cos, sine, cos, and sine that changes sign when I differentiate it. So I end up with minus sine x times sine x plus cos x times the derivative of sine x. And what's that? Well, according to that same mnemonic, it will just be cos x, right? I don't change sign. The ones that are most new to us, I guess, are these hyperbolic trig functions. And one particularly nice thing about them is that in terms of sine and cos, the derivative of one is the other. There's no changes of sign or anything to worry about. So that this expression here, I'm now I finished, right? I have an expression that's in terms of functions of x. So that will be my answer to part A. I had to look for these derivatives during the exam. I took out ways that I remember things like ddx of sine x is cos x. But yes, because this term the exam is open book, if you want, you can have your course notes open to the list of standard derivatives or standard integrals or whatever. And they'll come in handy, I'm sure. Of course, I always recommend, even in the situation of an open book exam, it helps to know stuff, right? To memorize stuff, because I'm just in terms of time saving. So it's good to have the fallback option, of course, of being able to check against facts you already have, but don't fall into the trap of checking every single little thing you're using, because chances are a lot of the things you're using you do already know are true, and you might lose a bit of time actually trying to check all that stuff that you didn't really need to. But if you do have time and you're going back and checking, then why not, since it's an open book exam. Okay, but so that's how I got solve part A. And now I want to move on to part B, which is asking me to find the integral of some horrible looking expression in terms of sine, sine, cos, and cosh. And I think the most important step here, and I mean part A is kind of hinting that, since this is labeled part A and part B, I might very well want to use my answer to part A in part B. And with not too much difficulty, I think I can see that this expression here looks very similar to the expression I just found in part A, right? In fact, it's just 3 times it, right? So it seems very likely that I'm going to need to use that fact. And so I might go ahead and do that. So I'm looking at this integral I. So I'll just write it out again. Another thing I'll point out here, 2 things. So first of all, if I always think it can be useful exam techniques to look ahead at all the questions, all the parts of a question before you attempt them. And if I had just solved part A and was moving on to part B and saw that the integrand looked very similar to my answer, but maybe there's a sign error, maybe in my answer for some reason I got a plus here instead, then I might think back to my answer to part A and say, actually, it would make more sense if this were a minus sign out here, because then it would help me in part B, and so then I might check that I've done all the steps correctly to get my answer to part A. And the other thing I was going to point out here is that this bottom limit of the integral, it looks a bit like 3 over 2 pi, but it's really 3/2 times pi. So watch out for that sort of presentation. I think this is sort of an anomaly. I think usually we would make sure that there was no ambiguity in the representation. Okay, so that said, so I know this is really 3. The integrand is really 3 So maybe I'll just say I equals this. So it's really 3 times what I found in part A, which was ddx of cos x sin x, right? And so I'm looking at the integral of the derivative of something, which I know by fundamental theorem of calculus should give that something back, right? So in particular, really what I'm looking at the integral of the derivative of this expression here, which means by a fundamental theorem of calculus, if you'd like, you can think of this 3 as being outside the expression. So this is going to be 3 times that expression there. So cos of x times sine of x evaluated from 3/2 pi to 2 pi. Okay, so this is just my fundamental theorem of calculus, part 2. I think the way to think about this is integration is sort of essentially the opposite of differentiation. And so I'm differentiating, so I'm doing something to this expression cos x sin x, and then I'm integrating, so I'm undoing what I just did to it. So I should be getting it back in some sense. And then fundamental theorem of calculus reminds me that I have to evaluate at the 2 endpoints and subtract the larger from the smaller from the larger. Okay, so that's essentially my answer, but I would just like to simplify it, right? So this is really going to be 3 outside of what? So I'll first substitute into pi. And then subtract what I get when I substitute in 3/2 pi. And can I simplify this any further? Well, yeah, I know that the cos terms will simplify quite nicely. So cos of 2 pi is, of course, 1. Cos of 3/2 pi, it's an integer multiple of pi, but it is a multiple of half pi. So that's going to be 0. So this is just equal to 1. This is just equal to 0. So in fact, this is going to be 3 times 1 times sine of 2 pi minus 0, right? You might wonder, can I simplify the sine expressions? The answer is no. You might remember just told us that there are really only 2 known exact values for sine and cosh, and those are the ones calculated at 0. So sine of 0 is 0, cosh of 0 is 1. That's pretty much all we have in terms of exact values for the hyperbolic trig functions. So in this case, I'm looking at sine of 2 pi. I don't know really what that is. I mean, I could write it in terms of the exponential expression, but it's some number, and it's probably just as nice to write it as sine of pi than whatever it might turn out to be. Oh yeah, just as a good point. So sine of log of certain values and cosh of log of certain values can be simplified to look nicer, right? But yeah, in the end, it sort of feels like when we're simplifying expressions, like what really accounts for being simple anyway, you know? Yeah. So Hugh asks, would you want the answer in exponential form? I mean, you could write it in exponential form if you wanted, but it wouldn't be telling me anything more, and it would be using up more space in ink or typing time or whatever, right? So it's about that in this situation. If this question went on further and was asking about things to do with exponentials for whatever reason, then maybe I would think, oh, I might actually make that substitution. But at this point, I think this is good enough, right? So I can stop here, right? I know it won't get any simpler than that. And so once again, I can type in my answers. Maybe I can shrink this a little bit. Okay, so the derivative we said is going to be this expression here, so minus sine of x times sine of x. So conveniently for us, maple notation for hyperbolic trig functions is exactly how it looks. You just type the thing out, right? So that's my expression there. Can I make that any larger? No. That's my expression. As always, I can preview it, and that looks right. That looks like what I wanted. maybe I should point out I should not type out exactly what I wrote, which was this without the multiplicables, because that is going to give me some sort of a syntax error, right? So again, I always think if it, in my head when I read this expression in yellow here, when I read this in my head, I say, well, it's minus sine x times sine x plus cos x times cos x. So when I'm typing it out, when I say times in my head, I type an asterisk to remind myself that those are required. Okay, and then what about my integrals? So we said, looks like the simplest form is just going to be, so again, I don't type 3 sine to pi or something, right? I've got to remember all my Maple syntax, so it's 3 times sine of 2 times pi, and in Maple pi, the value for pi is capital Pi, like that. So again, I can check my preview. Yeah, that is what I wanted. Okay, so I can click what I do. It turns out I did correctly. I think that's pretty much all there is to say there. I was wondering, I didn't think to check this earlier, if I could just type in what I found at this point here as my answer, because it is technically the same thing, right? Just less simplified. I don't think there's any reason Maple should complain about it not being simplified unless it's something I didn't consider. So if, for example, I left in the cos of 2 pi times that thing, I believe that should still be marked as correct. Yeah. So in this particular case, because it was automatically marked, and because I wasn't asked to simplify or anything, I could have just stopped at the line that I just used a blue arrow to highlight. I could have just typed that straight in. It would have taken a bit more time. Might have been a little harder to make sure I get it written correctly in terms of Maple syntax, but if I did, it would also be marked as correct. I simplified it because it was easy enough to do so and made it easier to type. But in this case, it didn't actually matter. So I guess that's another thing you might like to keep in mind. But otherwise, I think that's pretty much all there is to say about this question. Yeah, any questions from the chat or comments from Josh?
No, not really. I guess you have to be careful with simplification. Every simplification you do is a chance to make a mistake. So you want to make sure you get that right.
Yeah, that's a good point.
But I probably would simplify here too, just because I'd have to stop and think, just double check cos the cos of 3 pi on 2 really is 0. Because I'm often confused about
yes, true. Yeah, I'm always imagining the waveforms in my head to remind myself.
Yeah. So when I went pi on 2, the next one is 3 pi on 2. Good. Yep. So
yeah, exactly. Yeah.
there is a process in my head where I double check this. I'm not just remembering things. Okay. Let's move on to the next question. All right, so a big box of syntax at the top. That's just reminding you of all the hyperbolic trig functions and whatnot, and exponentials and logs. Don't think we need any of that for this question. All we have is this. Oh, sorry, I lost it. Where'd it go? So all we have is this function here, and we want to work out a limit. Now, it's already telling me I'm going to need to use L'Hopital's rule for this. So we do have some sort of indeterminate form. I just need to understand what it is. So the first part's trying to help me. It's saying that as x tends to 0, I need to work out what happens to the numerator, so this expression up here, and the denominator in this fraction. Now, I've got to be careful. When I first read this question, for some reason, I immediately jumped to x to infinity. I guess I'm too used to taking limits as something tends to infinity, but this is 0. Now, I mean, these are very nice expressions. They're actually continuous in x. At least this one is continuous in it. It'll be well defined for x around 0. It will be continuous around 0. So to really understand what's going on, I really just need to plug in x equals 0. So for the first one, it really is just going to be this integral, and this is an integral over an interval of 0 width that is 0. So this will just tend to 0. And the bottom's even easier. This is continuous. It's a cubic. Polynomials are continuous functions, so I can just put in x equals 0, and I can see that becomes 0 plus 0, so that also tends to 0. So that's what I expect. I expected to see something of the form 0 over 0 or infinity over infinity. And now it says we're going to write this as the limit of a ratio. Yeah, so we're going to write it as, using L'Hopital's rule, we can rewrite it as the limit of a ratio of two new functions. Now, I think the wording here might have confused people because you have to work out what these two new functions are. And from L'Hopital's rule, what you know is that this function on top, it should be a derivative. It should be the derivative of the expression in the numerator. It should be the derivative of this. And the thing on the bottom, well, that's going to be the derivative of that cubic, that derivative of x cubed plus 9x. Now, I think this is what confused people because there was no mention of a derivative here. That's something you're supposed to know about L'Hopital's rule. So the question didn't tell you this. You're supposed to know that these things are supposed to be derivatives of some expressions. Let's calculate this. Second one's easier, I believe, because you get 3x squared plus 9. Derivative of an integral. How do I do that? I think actually we just used it in the last question. Yeah, the first fundamental theorem. So this is nice. It's just an x. So it's actually just going to be the integrand evaluated at x. So that should be my answer. So it should be x power of 6 plus 25, and this should be x 3x squared plus 9. Is that 9? Yep. And now I can actually just take the limit of this ratio. So the ratio of these two things as x tends to infinity, as x tends to 0, and I get root 25 over 9. Or that should be 5 over 9. So I should be able to write this as 5 over 9. I think that's all the question asked for, so let's put it in. So the top tends to 0, bottom tends to 0. The top is the square root of x to the power of 6 plus 25. The bottom is 3 times x, 3 times x squared plus 9. Just double check. Oh, and the answer is, let's type it as square root 25 over 9. Now, yeah, so this previewer has a little bit of an issue which I need to fix before the exam happens, if I can. It's saying square root is just square root. I think I know what's causing this, and I think I can fix that, but this is correct. This one, it should complain, yeah, I'm missing an operator, so I need to fix that. So it's actually, as Sean was reminding us, this is 3 times x squared plus 9. That's what I meant. And this is just the square root of 25 on 9. That all should be correct. Yeah. And I can simplify that to 5 over 9 if I like. Both correct. Any questions in the chat? Or any questions from Sean? So yeah, I think the wording of this question might have caught a few people out, because you do these two new functions, they are derivatives of something. That's what L'Hopital's rule gives you. Oh, what do you do if the lower bound is different? Well, I mean, there are various ways you can do it. I mean, in general, you can prove the following. So if I wanted the integral from, say, some function of x up to some function of x, some f of x dx, So this is, one way to think about it is it's the derivative of an expression like this, f of b of x minus f of a of x, where the derivative of f is lowercase f. And let's say just in terms of t. So if you want to do this calculation, well, you can just do it using the chain rule. So this is going to be the derivative of f at b of x times the derivative of b of x minus the derivative of f at a of x times a of x, which is f of b of x times derivative of b minus f little f a of x times derivative of a. So it's not too hard to convince yourself that this is correct. So you just plug it in to what's inside. If it's the bottom limit, there's a minus sign. I mean, there's a lot of different ways you can prove this to yourself. Another way is to say it's the derivative from 0 to a of, it's the derivative from 0 to b. Minus the integral from a. Where actually you can think of minus this integral as the integral from a of x to 0. Think of this entire thing as plus that. So you do need to be careful. If there is something which is a bit different up here, you will get a slightly different answer. So for example, if it was x squared, you would end up with x squared to the power of 6, but then you times it by the derivative of x squared. There's actually a tutorial problem which is good for this. I forget its exact number though, but if you look at one, there's one which is all about taking derivatives of integrals like this, and you should definitely go practice that one if you haven't done it already. It is in chapter, I think chapter 7, should be in chapter 7.
Yeah, I remember that question too, but I don't remember the number. The other thing I was going to mention.
Any comments about this, Sean?
Yeah, I mean, nothing very interesting to add. Like what you said is exactly how I would, and I think how everyone would probably approach it. The thing about getting confused or stuck on the g of x and h of x notation, another thing you might have done is just started with the question itself that said we're going to find this limit using L'Hopital's, and so you may have just straight up done that. So if you did just solve it using L'Hopital's, then you would realize one of your steps would be that the limit equals the limit of something over something, and then you would realize that those somethings are your g of x and your h of x that you're looking for.
Mm-hmm. All right, next question.
Yep, sure. Okay, yeah. So for this question, we're looking at a polar plot. So I think I'm getting some feedback from someone. Just make sure that if you're not talking, that your mic is on mute. Okay, so we're looking at a polar plot here, and we've been given the function. It's this here, right? So that's going to be important probably. So a function. Remember, polar plotting is we're plotting in the xy plane, but in terms of r and theta instead, where r is essentially the modulus, right? It's a distance from the origin, and it's always non-negative. And theta is our argument measured from in the anti-clockwise direction from the positive x-axis, right? But we have a function relating r to theta, and it's being plotted here for us for some values of theta using this maple command, which it might help for me to actually pass what it's saying, right? So it's plotting r equals 6 theta, as it should, for theta between what and what. So for theta between pi on 6 and 7 pi. Okay, and that's my result. And the first part of this question is asking me to find the Cartesian coordinates for the point furthest from the origin. So we're talking about this point here in the plot. Right? So first of all, the question is, well, there's two things I have to worry about here. One is, how do I convert from polar form to Cartesian form, right? And the other is, well, what actually is my substitution I'm making to find this particular point? I'm just thinking, is it better to, well, yeah. So I might think about what leads me to this point here first, right? Clearly, this is some sort of continuous curve that's being plotted out as theta ranges from pi on 6 to 7 on pi. But I'm not sure which direction it's going, right? When theta was pi on 6, was I over here? Well, it's a bit hard to see what I'm pointing to here. Was I over here and did I spiral out as theta got bigger? Or was I over here and did I spiral in as theta got bigger? I mean, you can think about in various ways. You can come up with a good reason as to which it might be. In a worst case scenario, you could just substitute in both endpoints, because I know that this red point, which is the endpoint of the curve, is going to be one of those two endpoints, right? And then perhaps the results I get will help me tell, just by looking at the diagram, which point I actually care about. But on the other hand, I could think about, well, if theta is ranging from pi on 6 to 7 on pi, 7 times pi, then what's happening to r, right? So r is 6 on theta. So if I want to write this this inequality in terms of r, then really I'm talking about, I want to know not what happens to theta, but what happens to 6 on theta as theta ranges from pi on 6 to 7 on pi. Well, that sort of means so I'm thinking, what happens when this is 6 on theta? Well, I'm inverting all parts of the inequation, which means the signs will flip, and I multiply everything through by 6, essentially, right? So, okay, actually, let's write that out completely. So if theta, let's look on the left. So if theta is greater than or equal to pi on 6, then 6 on theta is going to be less than or equal to pi on, so I flipped and then I multiplied by 6. So I think that's what I want there. Oh, sorry, what am I talking about? Okay, so what I'm doing is I'm inverting theta, and then I'm multiplying through by 6. So I want to invert this left-hand side, so I want 6 on pi, and I want to multiply by 6 as well. So I'm going to get 36 on pi over here. Okay. Yeah, as Josh says, I probably should have broken this into parts and thought about just what happens to 1 on theta, and then what happens when I multiply 3 by 6. And what's happening on the right here? Well, I'm flipping and multiplying by 6 again, so I'm going to end up with 6 on 7 pi here. Okay, so but really, as I just said, 6 on theta is really r. So actually, what happens is that when theta is very small, theta is much larger, when theta is small, r is large. And when theta gets larger, r gets smaller, right? It goes, so as theta ranges from pi on 6 to 7 on pi, r ranges from 36 on pi to 6 on 7 pi, right? So it's something bigger to something smaller. And that tells me that actually I'm looking, for this red point, I'm looking at, which is the end point of the plot. So I'm looking at either theta is pi on 6 or theta is 7 on pi. I must be looking at theta is pi on 6 because that corresponds with r being 36 on pi, which is 12-ish, I guess. 36 on 3-ish, so 12-ish. Not r being 6/7 pi, which is going to be something smaller than 3, which would correspond to some point somewhere in here, right, in the center. Okay, so I have my values for theta and r, but I want the Cartesian values for that point. I want x and y. So the other thing I need to remember is how to convert between the two. And that's something that I recommend having just committed to memory, right? That x is r cos theta in terms of r and theta, and y is sine theta. Oops. If you are not 100% sure, well, okay, it's open book, so you can probably just check, right? Or you could just say, okay, well, I measure theta from the positive x-axis like this. So if I'm looking at some point over here, then its x-coordinate will be the adjacent side of this triangle I've written over the hypotenuse. That is, it should be cos times the hypotenuse, which is r, right? So anyway, but most likely you have just committed these conversions to memory. And so now it's just a matter of substituting in the values for r and theta that I'd like. So in this case, my r is 36 on pi, and my theta is pi on 6. Okay. And can I simplify this further? Well, yeah, because I know that pi on 6 is a special value. So again, in the open exam, I could probably just have a lookup table at the ready, or I can just remember my special triangles. So pi on 6, I remember, well, it's not pi on 4, so it's not the isosceles triangle I care about, so it must be half the equilateral triangle I care about, where the values must be 1 and 2, and so what's left is root 3. Pi on 6 is the smallest angle in that triangle. So if I'm talking about cos of that, I want the adjacent on the hypotenuse, that is root 3 on 2. So this will be 36 on pi times root 3 on 2, or if you like, 18 root 3 on pi. And I can do the same for y, so it should be 36 on pi times sine of pi on 6. And again, looking at my little triangle, I know that in this case, sine of pi on 6 is 1 on 2, or I can write the whole expression as 18 on pi if I like. Okay. So those will be my answers to part A. So I found x to be 18 root 3 on pi. And I found y to be just 18 on pi. And if I like, I can check that makes sense. So, well, 18 on pi, that's 18 on something a little bit bigger than 3. So I expect something a little bit smaller than 6 for my y value, although the y-axis isn't labeled. So, but can I? Yeah, I can kind of see. So because of the concentric circles, I know that 6 is here on the y-axis, and yeah, that point does look like its y value is approximately 6, close to it anyway, right? And similarly, x is 18 on pi times root 3, so it should be about 1.5 times. Thinking of root 3 as about 1.5, which is not great, but if I think it was about 1.5 times 6, then it should be near 9. It's a little bit larger than 9, but I did expect it to be a little bit larger than 9 for the x value. So those seem to match. They seem to work out. So I'm pretty happy with my answers for x and y here. Okay, so I can move on to part B. And for part B, we're talking about what happens to this graph at some limit, it would seem, right? So it says that the curve is going to approach a horizontal asymptote. It makes sense that that horizontal asymptote must be going like this, right? It must be heading to the right. So because as theta gets larger, this spiral is kind of, sorry, this curve is spiraling and further towards the origin. As theta gets smaller, we head outwards, and the claim from part B is that actually this will become this will approach a horizontal asymptote. So we want to find what exactly that asymptote is in terms of y equals some constant. And it looks like it might be something close to 6. So I could also use that as a possible sanity check once I find my answer. So, but what am I really looking for here? If I want to find, so first of all, we said that this is happening as theta gets smaller, as theta gets smaller, r gets bigger, and so we get further from the origin, right? So really, I'm talking about what is the limit as theta goes towards 0, right? I guess from the positive side, since we can't have negative theta because we can't have negative r, right? So I'm really looking at the limit of y as theta approaches 0 from the positive side. And of course, y is r sine theta. So that's the limit of. Sorry. It's just of r sine theta, right? That's what y is. But of course, we also have our formula that relates r and theta. So we know that r can be written as 6 on theta, which looks a little more familiar to me, I think. So this is 6 times sine theta all over theta. Yeah. So why is this a good sign? Well, because I know we learned early on that the limit as theta approaches 0 of sine theta and theta is a special value. It's always 1, right? So actually, this is just going to be 6, well, times 1, right? So 6. Rishan asks, why is the horizontal asymptote when x? So it's when theta gets smaller, not when x gets smaller, right? But well, why is that? It was sort of from my analysis up here, where I was looking at, or I can even just look at this expression, really, right? So the asymptote is, its behavior at as something approaches infinity, right? So if I think in terms of r and theta, well, I don't know much about what's happening to as this travels further to the right. I guess theta is getting a little bit smaller over time. But I think it's much clearer to me to think about what's happening in terms of r, the distance from the origin, because as this blue curve goes further and further to the right, that's because r is getting larger, right? The distance from the origin is increasing. So really, I'm saying what happens as r approaches infinity, right? But that's the same as saying what happens as 6 on theta approaches infinity. That is, what happens as theta approaches 0 in this case. Does that make a bit more sense? That's the way I always like to think about polar curves is, does thinking about it in terms of r or theta help more? And then which direction am I going as one of them gets, as r gets larger, say, or as it gets smaller? In this case, I've established as r gets smaller, of course, I'm going to spiraling closer to the origin. As r gets larger, I'm moving further away, and that's when my asymptote apparently is going to happen. But that happens since r is 6 on theta, r getting large corresponds with theta getting small. Yeah, cool. Okay. So, and then it's just a matter of making the right substitution. So again, I needed to remember that y is r sine theta, and then replacing r with something in terms of theta gave me an expression only in terms of theta, which I needed because I was talking about the limit as theta approaches 0, and it happened to be a known limit. So that's all I need. It tells me that my answer is in fact 6, right? So the horizontal asymptote is y equals 6, and yeah, I can check my diagram. It does look about right that if I line through y equals 6, that curve could very well be approaching that as a horizontal asymptote. Why is 6 not 0? I'm not quite sure. Is the question why is a equal to 6 and not 0? Right. So, well, okay. So first of all, look at the way the question is worded. It's saying that it's approaching some asymptote y equals a, right? What does y equals 0 look like? Well, that's this line here, right? I don't think the curve is approaching that as an asymptote just by looking at it. So that's the first sign that that's probably not what I want. Oh, okay. So maybe you're asking how do we get to this derivation? Well, it's a known value essentially. It's one we encountered in lectures that in general the limit let's not use x of t as t approaches 0 of sine t on t is 1. I'm trying to remember how we proved it. I think we used squeeze law. Is that right? Does that
Did a
work?
geometric.
Oh, okay. Sure. Yeah.
It was a pinching one. I mean, actually, in terms of calculating, you can use L'Hopital's rule. You couldn't use it in the first problem we encountered it, because in the first problem we didn't actually have a derivative of sine at that stage. We were trying to find the derivative of sine. But at this stage,
Yeah.
you could verify it with L'Hopital's rule. It is a true rule.
Yeah. True. So L'Hopital applies always. I think. Yeah. Yeah. So if you like, it's a bit of overkill because it's a known limit. You're allowed to quote it essentially. But if you'd like, you could use L'Hopital because as theta approaches 0, the numerator approaches 0, the denominator approaches 0. So I'm looking at an indeterminate form, 0 over 0, right? So I'll differentiate top and bottom. So that will give me cos theta on the top and 1 on the bottom. And so I could just evaluate this at 0 and it's 1, right? So yes, limit of sine theta and theta is 1.
Towards infinity, though.
Yeah, so remember that t is approaching 0 here, so we have to be a bit careful. Yeah, I'm sure there are many ways that we could derive this thing. But it is true that you can just quote it. You can just write straight up that we know that the limit as t approaches 0 of sine t on t is 1. But yeah, you can use L'Hopital. I think you can think of, yeah, the geometric argument is the nicest because it uses the most basic setup, I think. But yeah, I mean, so I guess in a sense this comes from practice. But as soon as I saw this in my expression, I knew I was finished because I know what that limit. Well, if I approach 0, I know what that. I've seen that limit before. You know. Oh, yeah. This limit as t approaches infinity is undefined. Oh wait, is that true? Oh no, actually yes. You could use the squeeze law for as t approaches infinity for this, because sine on t is not well behaved as t approaches infinity. We can't say much about it, but it is bounded by -1 and 1. Okay, yeah. So that's the situation there. Mostly this is just a problem about converting between Cartesian and polar form. I wanted to point out that it's useful to use this if you're given a diagram. I mean, if you're given any maple output, it's probably going to be useful to use it, right? We had to use the actual command here to know what the values of theta was ranging between. But also, why not use the diagram to help us? I was able to sort of give a sanity check that I found the right Cartesian coordinates and that I found the right asymptote here by doing that. Okay, so again, we can type in our answers here. What do we find? Let me just scroll so that's readable. I think we should all be quite familiar with how to do this stuff by now, right? So this is going to be 18 times, right, asterisk, right? Square root of 3, which I just typed like that, and it's divided by pi. And I remember that in Maple pi is always capitalized if I want it to represent the special value. And similarly, y is just 18 over pi. And I remember again that pi should be capitalized. I think so that my preview, it doesn't show the square root symbol, but it does confirm that I've got pi correct, and that my fraction looks like how it should. So that's all good. And then there's nothing really interesting here. A equals 6 is my answer. I also, for this question, we're asked to explain how we found that value of a. So I would just type out what I did over here under this blue line. Maybe I'd say a little bit more than that actually. So I'd say the asymptote is approached as the curve moves further from the origin, that is, as r approaches infinity, since r is 6 on theta, r approaches infinity as theta approaches 0 from the positive side. Not that that's important in the end here. Maybe I'll space this out a little bit so I can see what I'm typing, and maybe I will make it a bit larger so that everyone can see what I'm typing. Oh, whoops. Okay, so we want to find the limit as, so sometimes these things are a little bit tricky to type. So I could write the limit as theta approaches 0 of y, right? Or I could just write this in words. The limit as theta approach, well, I could even write approaches 0 of y, right? I think that's readable enough. I could throw in brackets there if I wanted. I could use a mix of symbols. I mean, you certainly wouldn't do that in an assignment or something, but in this sort of situation, if it makes it more readable, why not? But really, of course, this is the limit as theta. Well, yeah. So at this point, I might y is r sine theta, which we know is 6 over theta cosine theta. Which I might even write even more clearly. It's 6 times on sine theta. So limit. Oh yeah, I'll write it this way. This time theta approaches 0 of that thing of y is going to be 6 times 1. Let's use t. Something like that would be a satisfactory argument, I think. Will this answer up? So I mean, none of these expressions that I'm using, like, I mean, I don't. Yeah, so I'm typing asterisks because I've become accustomed to doing that, right? None of these things are like rendered in MapleTA when the marker looks at them. So you don't have to worry about this coming out wrong. Like we have to worry up here when we're entering numbers, right? So if for example, I wrote 18 pi instead of 18 times pi, right? If I write that in an answer box, that would be a problem if I wrote this one because I wouldn't get the marks. In this sort of essay box, nothing is rendered. So whether I write this first thing or the second thing, or even 18 pi like that or something, it's all just rendered as text, and the marker reads it like that. So as a human, I recognize that all of these things are meant to mean the same thing, and so I'm not going to penalize. You're not going to be in trouble if you forget your Maple syntax, all these sorts of things. But Maple syntax can be useful. If I want to talk about exponential or something, it's probably easier for me to write x whatever than it is to write e to the power of. But I mean, it's not that bad, but it's a little bit easier to read, I think, being familiar with Maple notation, things like that. But you can also type it all out in words if you prefer, right? You're free to type however you like in this sort of problem. So yeah, maybe I didn't need to put to the power they wanted to be fancy, I could actually like aesthetically edit my answer. I could find the symbol for infinity and put it in here. Is that in this list? I'm not sure. Oh, here it is. So I could do that, right, if I wanted. If I think it makes it more readable or whatever. In the interest of time, it's probably quicker for me to type infinity. I don't know, actually. Yeah, it might be a tie between whether it's quicker to type the word infinity or just put the symbol in here, actually. Yeah, and then if I was being really clever, I might have started by saying, from here, we will write t instead of theta or something, right? Then I could have saved a bit of time by replacing my thetas with t's, something like that. Yeah, it's sort of a free-for-all in terms of the essay boxes. Yeah, don't worry about the format when you're giving these explanations. The formatting, that is.
What to be worried about is where, for example, Sean wrote 6 times theta over sine theta.
Yeah.
That should be 6 times sine theta over theta.
Thank you. Yeah.
So that's what we're looking out for when we're reading.
Yeah. You can point that one out. Yeah. Yeah. If I were marking this question, I would probably not have penalized for that mistake because I can see what the student intended based on the fact that the representation that's correct appeared twice, right? I mean, depending on how many marks this thing is worth. If it were worth, say, 3 marks, maybe I would dock a mark. If it were worth 1 mark, I wouldn't give them 0 out of 1, you know? But yes, it's always good to proofread what you've written to make sure it's actually correct. Okay, that's probably all there is to say about this one. Shall we move on to 14? Oh, right. Jed's asking, like, will we post answers? Is that your question? I don't think so. I think these videos are basically serving as our model answers to these questions. Yeah, I'll let Josh continue with question 14, but you can elucidate in the comments if you were asking something different. Josh, is your mic on?
Sorry. I'll start from the beginning. Where was I? Yeah, I forgot to unmute it. All right, so yeah, so what I was saying is a lot of these questions, they have stories, little stories that they're telling. So for example, here you have a person called Alessandro, and he's trying to implement a derivative. Now it does say this is an incorrect expression. So the following thing that this person has written down is not correct. Now, unfortunately, there was one student, I was reading over the comments this morning, who did quite rightly point out that this isn't the expression you would get for the derivative, but that was the point of the question. And they put a nice comment at the beginning of the exam. I don't actually know if the marker for that question saw this because that answer was actually the perfect answer for the end of this question. So make sure you don't just look at the calculations. If there's a bit of a story, try and work out what the story is about. So this is an incorrect expression. This is not the derivative. We don't expect what we're doing here to give us the correct derivative. All right, so it's trying to really lead us through. It says, well, for this expression here, what is this? What is this value? Now, there's nothing really special here. You're just expected to realize that f of x plus 4h is going to be 5 times this thing, 5 times x plus 4h squared. Now, you could expand that. I don't think you need to. You might need to for the next part, but for here you don't need to. And this one is x minus 4h squared. Now, we want to compute a limit. So the function which we're going to compute the limit for is going to be this expression here, which means we need to simplify this. Now, here's where it probably does help to expand it. So this is really f of x plus 16, no, sorry, plus 8h, 8xh plus h squared minus 5x, I'll get my x squared, minus 8xh plus 16h squared. All of that over h. Now, I don't think I need to simplify it, but I am doing it because it's what I need for the next part. So it's really nice. This term and actually this term cancel out, and we get 40xh. In fact, I think it's even nicer than I thought, because this term and this term also cancel out. So it's just 40xh plus 40xh over h. It appears to just be 80x. That's interesting. Doesn't even depend on h. So that's nice, because the limit as this goes to 0 will just be 80x. It's much nicer than I thought. Okay. So that's just the calculations. I don't think I need to simplify it like this, so I'm going to try that later, see whether that works. I think I could just plug it in. But it does make it easier to calculate when I do that. Now, what happens is our character, Alessandro, he tries his function. He has this limit. So this is a way to take a function and give you another function. And it's always a multiple of the correct result, what it should be. And the question is, why should this character have expected that? So let's actually look at the correct result. So we know that the derivative of 5x squared, we know that should be 10x. So this is 8 times too large. His answer is 8 times too large. Now, why should he have expected that? Well, let's go back and actually think geometrically about what's happening here. So if we look at this, well, this doesn't look so bad. This is a difference between two values of our function. So let's just try and think about what's happening here. We have some point x plus 4h, x minus 4h, the sum function, and our person, Alessandro, has calculated this height. So this difference is going to be f of x plus 4h minus f of x minus 4h. Now this is kind of how we went and defined the derivative before. We were looking at a slope as we kind of moved in towards the point. We were looking at a slope like between 2 points like this, but this idea is still good. It's still just a slope, and we're letting these points come towards 0. So yeah, I think Mohammed had a good comment. Really what we need to be looking at is, if we're trying to calculate a slope here, the slope of this line here, it should be rise over run. So rise, we already said what the rise is. It's going to be the difference between these two. This is what Alessandro used. Nothing wrong with that. But the run, well, that should be this distance here. Now, however you calculate this, you could do, for example, x plus 4h minus x minus 4h. But you should calculate, it's actually 8h. So if we really wanted to look at the slope should be this divided by 8h. And if we look at the original expression, it's missing that 8. This is missing from the original expression to make it the correct slope. So I need to write in something along those lines. So let's actually go to Maple, TA, try and write in our answers. First things first, we just want to enter this. I think I can just write this as 5 times x plus 4 times h squared. I have too many brackets, as it says. Good. This one's actually very similar, just with a minus sign. Now, I think, I'm going to do what Sean said. I'm just going to put these brackets in. I'm looking at this expression minus another expression over h. So not actually simplifying anything. That would be what I would answer. And that limit, well, that limit is going to be 80x, and 80 times x. So see how I did up to this point? So yeah, this is correct, but apparently it should also just be the same as 80x. But I can just do 80x. That's literally algebraically what it's equal to, but this one is also fine. It's just harder to understand. All right, so let's try and explain why Alessandro's method always gives a multiple of the correct derivative. So what should I say? So the correct, maybe make this larger. The correct way to calculate the slope over the interval I can't remember the word is. Well, let's say the correct way to calculate the slope would be using the expression f of x plus 4h minus f of x minus 4h over 8h. So the length of that interval, let's say the length of this interval is h. Okay. Since Alessandro used so since he used that, he used the expression without the 8. Calculate the slope. His answer will be 8 times larger than the correct answer. I might just center those to make them easy to read. Now, the only thing I have to think about to maybe improve this is to say the slope over what. So I might do this for the line joining 2 points. So the point is x coordinate x plus 4h and y coordinate, oops. So that's more than enough detail, I think, to satisfy a marker. But you're saying that, yeah, that thing on the bottom, he should have divided by 8h. Now, I will say a lot of people, when I read over solutions for this, they kept saying that this thing was 8 times too large. But I can't really, I mean, that's something it's a bit hard to say because it's hard to relate a function value like these x plus 4h's to just x plus h. It's very easy to relate this thing on the bottom to h. It's exactly 8 times h. And since this one is missing the 8, well, that's the answer. Any comments, Sean, or any questions from the chat?
Not really. I was just going to say for that part B, where you got like the answer turned out to be independent of h. That was sort of coincidence, I think, based on the fact like that the randomization gave you plus 4h and minus 4h as the terms. It was possible in this question to get terms that didn't match, like plus 3h and minus 5h or something, in which case your answer to B would have some term in h, and it would look different to your answer in part C.
I think some people might have gotten 80 times x plus some number, like I can remember 3 times.
Probably the difference of the coefficients or something. Yeah.
Actually, it's like that because it was you had a h. You ended up with a h squared over h in the end, which was just a h. So I think some people might end up with an answer that looks like that if you do the simplification. But as we saw, you don't need to do the simplification, which kind of actually says more about this question than it does about. Anyway, you still need to, I think, do the simplification yourself. So Hugh had a question. Could use the property that the limit of the limit of a function multiplied by a constant is equal to the limit of the function multiplied by the constant. Yeah, that's essentially what's happened here. I didn't mention the limits at the end, but that's what's going to happen here because this number is 8 times too large. So when you take the limit is 8 times larger. I didn't feel the need to mention that. I kind of thought that would be obvious for people. It's really, yeah, it's just, this quantity itself is 8 times too large. I don't think that's true. So someone's asking, can I write f of x plus 4 equal to f of x plus f of 4h? I think that's what I'm hearing. This sort of fact would only be true for a very special function. And I wouldn't expect it to be true in general. In fact, it's not true for our case. So no, I wouldn't try to talk about anything like this because this is just wrong.
Yeah, if we were allowed to split functions up like that, then calculating the derivative from first principles would never be interesting.
Yeah, that's kind of true. Yeah, I think maths shouldn't be that easy in some sense. So no, I wouldn't do anything like this. That's just wrong. Any other questions? Well, I think maybe go on with the second last question.
Yep, sounds good. Cool. Yeah. Okay. So, question 15 we're looking at here. This one is essentially, in some ways, it's sort of a curve sketching question, right? We focus on curve sketching a bit in the calculus course, but as some of you noted in the chat during those lectures, it would be a thing to test in an online exam. We can't. I think actually it is very loosely possible to ask students to sketch very simple things as solutions. but as parts of this question sort of demonstrate, it is also possible to ask you to sort of do all the steps required to be able to properly sketch something without actually having to sketch it. So the function we're looking at here has this expression here, and the first step is asking us to find its natural, well, a domain for it, right? So we sort of want to think about what would its natural domain be, and then what do we have to do for this restriction, right? Where f is being defined as being from some domain I, and I is the largest possible domain that includes 216 in it. Okay, so first things first, I'm thinking, well, this is my expression. When is it well-defined, or more specifically, when isn't it well-defined, right? And really, there's only one situation where this is not going to be well-defined, and that's when the denominator is 0, of course, right? So we know that there'll be discontinuity. Well, I'll say when the denominator is 0. That is when x to the third minus 3 is 0, right? Well, that's the same as when x is 27, right? As in when x is 3 cubed. And that'll be the only real value x for which the denominator is 0. And otherwise, it should be well defined, right? Yeah, so we'll leave it at that for now. So if I'm thinking about, if I'm imagining what this sketch is, it's often going to be useful. Even if I'm not asked to draw it, I'm going to draw it because it's probably going to help me. I know that something funny is going on at 27. There's a discontinuity here for however my curve looks. And I could also ask myself, what does it look like when I'm close to 27, when x is close to 27? So if x is just a little bit larger than 27, then my denominator is just a little bit larger than 0. When x is just a little bit less than 27, my denominator is just a bit smaller than 0. So I'm looking at, it would seem I'm looking at something that I'm looking at a vertical asymptote here, and that my graph is sort of going to be, my curve is going to be approaching very large values as I get closer to 27 from above, and very small values when I approach it from below. And other stuff may go on from there, right? All this to say, I know for sure that there's a discontinuity at x equals 27. There shouldn't be a discontinuity anywhere else because there's no odds for this function to fail. And so if I'm talking about natural domains, I'm looking at this side of 27 or this side, right? With 27 excluded. And importantly, I want the interval in my answer to be the one that includes 216. And of course, 216 is greater than 27, right? It's somewhere way over here. So I want this interval, right? The one on the right. So it would seem that the interval I want goes from, well, it goes from 27 and increases. So it goes from 27 and up. It's, I guess, what I want to say, right? To include 216, not everything below 27. How do I write that as an interval? Well, I'm going from 27 to infinity, essentially. Is 27 included? No, it's not. It's a discontinuity. The function literally isn't defined at x equals 27, so I shouldn't include it in my interval. And of course, infinity is not a number, so I have an open bracket on that as well. So my interval in interval notation will be exactly that, right? 27, comma, infinity, both with using round brackets on both ends. Okay, so that's the first part dealt with, I think. For part B now, we are focusing on a sub part of that interval. Oh yeah, that's a good point. Something that Josh has mentioned in lectures, right? Is yeah, let's just say undefined. So without context, if I look at this graph and I see that it kind of skips values at, it doesn't occur at 27. It looks, in terms of the curve, like, well, it's a discontinuity, right? The curve doesn't continue as I travel at 27, but also the function is defined at x equals 27. So it doesn't quite make sense to talk about it being continuous or not at that point. Okay, so next thing I want to do, right, is focus on a subinterval. So I'm looking at, so I'm going to not worry too much about scale here and talk about the interval that we're focusing on here, which is this part here. So we're looking at, we're going from 27, but not including it, all the way up to and including 216. That's our interval that we're interested in for this part, right? And we know that the function is well defined over that because it's a sub-interval of the interval we had in part A. And so we'd like to know its behavior. In particular, we want to find the minimum value that is attained over that interval. And how to do that? Well, I'm going to want to think about the derivative probably, right? So let's make some space over here. So I remember that my function looks like this. And I don't know, again, I prefer to write, well, actually, let's talk about f dash x. So I'm looking for ddx of 1 on x to the third minus 3, or I might prefer to write it like this. I don't know, maybe that's not more useful, but I like to avoid fractions if I can help it. So what is the derivative of this thing? Well, it looks like I'm going to be using the chain rule here, right? So I want to treat the function in x, like so I've got some function in x to the minus 1. So first I'll just differentiate the function in x as its own chunk, sort of thing. So something to the minus 1 differentiated should be minus that something to the minus 2. But I have to make up for the fact that my something was not just some linear term in x by the chain rule multiplying by the derivative of that block, that something. So I also need to write out the derivative, or maybe I'll just say times ddx of that thing. Right, and probably you're used to not having to worry about these intermediary steps, but just making it clear here. And then, so what do I get here? I'm looking at x to the third. So I'm going to have 1/3 at the front times x to the minus 2/3. Okay, and then maybe at this point, I would like to go back to fractional representation to see exactly what's going on. So this is going to be minus 1/3 outside of, or just all over, I guess, x to the third minus 3 squared times x to the 2/3. Okay, all right, that's my expression for the derivative of f. What do I want to know, having found it? I'm looking for maximum, minimum. Well, in this question part, I'm looking for minimum points. That means I'm looking for critical points, right? And that means I'd like to know when is the derivative 0. But if I look at this derivative, I can pretty quickly see it's never 0, right? The numerator is always 1. So I'm never going to have it be 0 times something. It's undefined at certain points, right? The denominator can be 0 when x is 27, which we've already ruled out, or when x is 0, which is not included on my interval anyway. So it seems like there's nothing, there are no critical points to talk about in terms of the derivative, at least. Is there anything I can say about this derivative? Well, there's one very important thing to note, I think, and that is that I don't expect any turning point. I haven't found any cases where it's 0. So it's probably always going to be one particular sign. And yeah, as Aaron has pointed out, this value is always negative for the interval we're looking at, right? Because if x is always greater than, well, actually, So this term here is being squared. So no matter what it is, it will be positive. Similarly here, I guess, right? Because this is x to the third squared. And we're only dealing with positive values of x anyway. If you want to be super careful, you could say, well, x is always greater than 27. So this term being squared is always positive. And so is this term here. So yeah, in particular, this is strictly greater than 0 for all x in my interval, which was 27 up to 126, I think. Oh, 216, whoops. And yeah, so that means, as we know, that the function itself is decreasing over that interval. So whatever it's doing, it's always getting smaller. Well, it looks like it's going to end up horizontal. That's not necessarily true. There are no turning points to speak of, is the point. So in that case, the graph looks something like this, I guess. And what then is the minimum value obtained on that interval? Well, it better be this point here, right? So we know that critical point, like the points we care about when looking for maximum and minima, the cases where the derivative is 0 and are undefined, and where at the endpoints of the interval, if we're dealing with a closed one. Well, yeah. So in this case, I also want to check what happens at 27. Well, actually not really, because 27 itself can't be substituted. But also at the other end at 26, which is counted in my interval. And so I think I can see pretty clearly from this diagram that the minimum value is obtained when x is 216, right? So I can say my minimum value is at x equals 216, which is when f of x is f of 216, which is what? So where's my expression? 1 on x to the third minus 3. And I happen to know that that's 6 cubed over there. So 1/3 will be my answer. Yeah, hopefully that all makes sense. Yeah, I guess again, this is an open book exam. You could, if you wanted, just plot this thing in Maple to check that these deductions make sense. You would still need to explain what's going on in this explanation part at the bottom. So you're not getting away with anything by just plotting it straight off, but that would be a valid option to check that what you're doing makes sense. Okay, let's finish this off here. So we just have some yes or no questions now. Does f have a maximum on that interval? Well, by the same argument, we know it's decreasing. We know there are no turning points over the interval. So I really just care about that. The other thing I care about are the endpoints. I know that when x is maximum on the interval, because it's decreasing, I'll obtain the minimum value. And so when x is minimal on the interval, I should obtain the maximum value, right, for f. But of course, I can't substitute in 27. It's an open interval at 27, which means that x can get as close to 27 as I like, as long as it's larger than it. And the closer the larger f will be, but I'll never have a definite value of f, which is the largest for that reason. So it's a little bit hard to argue, I guess, but we can do that in part E, right? But the thing I think is clearest is that as x approaches 27 from above, f of x is approaching infinity, as we sort of argued earlier when we were looking at this function in the first place. So no, it's not going to have a maximum, right? It'll get larger and larger as x approaches 27, but it won't be an actual value that is its largest possible. Okay, so D, does the maximum minimum theorem apply? Well, what do I think about that? I know the maximum minimum. So there are a couple of ways to think about this, right? I could just remember the maximum minimum theorem, right? What are the conditions for it? It says if f is continuous, on a closed interval AB, then stuff, right? What is that stuff? Well, then the max and min are obtained, right, on the interval. But so for me to be able to apply the maximum theorem, I need this if condition to hold in the first place. Is f continuous on this interval? Well, yeah, it is. But is the interval closed? No, it's not, right? The left side is open. 27 isn't included. So I'm not dealing with a closed interval. That's enough for me to know that the maximum min theorem won't apply, right? Alternatively, I could look at my previous answers, right? I found a minimum, that's fine. But I also found that I can't find a maximum. So if the maximum minimum theorem did hold, I should be able to find a minimum and a maximum. But we already argued that we can't find a max. So it would be very surprising to then say that the maximum minimum theorem does apply, right? So the answer should be no there as well. Okay. So I was looking at, so Hugh's asking about the differentiability of the function. So this is this funny situation again where we worry about the endpoints, right? Yeah. So on this interval, well, I should make sure, and I should check in with the expert, namely Josh as well, right? But on this interval, since 27 isn't included, we found the derivative, and it's continuous for positive value, well, values greater than 7. So yeah, it should be differentiable on the interval, I think. But I'd always be going back and consulting my definitions in my notes to make sure. But we're not talking about differentiability here, right? The maximum minimum theorem only requires that f be continuous. Okay. Oh, and then Henry asked, what if 27 is included? Well, okay, so for this particular function, 27 simply can't included, right? 27 is not in the natural domain. If this were if I didn't know what the function was, right? If I was just told f is some function and it's continuous on the closed interval, 27 to 216, if I know those two things, that it's continuous, and in particular it's continuous on a closed interval, then maximum min theorem applies. And I can say with confidence that I know a maximum min are obtained, right? For this particular function, I can't write this because I can't include x equals 27 on this function. So it would be nonsense for me to talk about the closed interval for this particular function, like including 27. But yeah, in a general case where maybe it is defined at 27, then be able to say that a maximum is reached, right? So if I knew that it was that value at 27, right, then because it's continuous, I would know that it has to do something like this at some point, and so there's some maximum that it must obtain, right? But none of that's true for this particular function. Yeah, that's right, Henry. Yeah, so we don't want to talk about so yeah, right. I guess you could talk about an interval like this. But that's also not closed, right? Because it's missing something in the middle. It's missing a point. And so we wouldn't be able to talk about continuity over that interval either. Oh yeah, in fact, yeah. Terminology-wise, that's a union of two intervals, right? Of disjoint intervals. So it's not an interval itself. Okay. So yeah. So whoops, sorry. So again, we can type these things in. B is very easy, it's 1/3. A is a little bit more interesting. We need to use interval notation, and I haven't had to do that in Maple before, so I might check this big green box up that tells me exactly how to do it, right? It says to use square brackets and round brackets like you normally would. it says to use like the word infinity for the value, the symbol infinity. That's probably all I need to know to be able to do this. So I know that it should be open interval at 27 up to the open interval at infinity. So it should look something like that. Okay. Does it have a maximum? No, it does not. Does it theorem apply? No, it does not. And then this last part where I want to provide reasons, well, we've already talked through them, right? So part C, remember, said, does it have a maximum? And so the argument we decided on was to say the derivative of fx was where it was. Where did I write that? Over here somewhere. But maybe this might be the first time that I might actually think of preferring the equation editor over trying to type this out properly. But it's something like this, right? -3 all squared times x to the 2/3. I think that looks good. I think that's readable-ish to me. Yeah. So, so maybe I might go into a little bit more detail, trying to make it a little bit clear what I'm writing here, right? But the important thing is this is negative all x on the interval, which is 27 up to 216. So instead of me writing the derivative of f of x equals, which looks a bit dodgy, I might just write, I might say it like this, is equals, something like that, maybe. So in particular, right, f of x is decreasing. Decreasing. So that means that if a maximum value is obtained, it occurs at the minimum value for x on the interval. But there is no minimum value. Interval since it's opened out on the left. Something like that, right? Or alternatively, you could say the limit, right? As x approaches 27 from above, of f of x is infinity. And you could give a little bit more of an argument as to why that is true. But that tells me that if f of x approaches infinity, it's not going to have a maximum, right? So that explains part C. Maybe I'd even say part C. And then what about for part D? So that's, remember, where we're showing that the max-min theorem doesn't apply. So I might say, I'll use the proper explanation, right? So the max, oops, why am I no longer in large size font? The max-min theorem only applies if the function is continuous over a closed interval. The interval 7 to 16, like that, is not closed. Theorem won't apply. Okay. Or you could just say we have already shown that there is no maximum on the interval. So I could say maximum theorem won't apply because since it implies a max would exist, or something like that, right? Yeah, so some sort of argument like this is, I think, would suffice. Are there any questions or comments? Catherine, I mean, I just separated them out to make it clear that I've answered both parts. You don't need to, right? Markers are going to be combing your answer to see how many marks they can give you, right? We're not trying to take marks, we're trying to give them away. So you don't have to format it like this. So long as you kind of make it clear that you've addressed both parts in some way, that would be sufficient. Yeah. So if it were in a rush, after I showed parts, I could say, thus, the maximum theorem doesn't apply because there's no maximum.
If there was a maximum, would the maximum theorem apply?
Yeah, that's a good point, right? So because there isn't a maximum, I know the maximum theorem wouldn't have been at all useful to me. If maximum theorem applied, I definitely know a maximum min exists. The converse is not necessarily true. If I know a maximum min exists, I don't know that I can apply my maximum theorem necessarily. I'm trying to think of a counterexample though. So is there something where actually maybe the converse?
It's a continuous function with a max and a min. I mean, take the function which is 1 for x positive and 0 for x less than or equal to 0 on any interval, any closed interval containing 0 that has a max and a min. In fact, for any closed interval that has a max and a min. But it's not continuous, so the theorem didn't imply that.
Right. Yes. Nice. Okay. Yeah. So the continuity thing. Yeah. Cool. Okay. Yeah. I was thinking about the interval being closed, but yeah. It would have to imply all things. Yeah. So Josh's example would be a function like this, for example. Any interval I take. Oh yeah. Even any open interval. Yeah. We'll have a max and a min for sure. So max and min exists, but that doesn't tell me that the thing is continuous. It doesn't tell me that my interval is closed. So I can't quote the converse of max min theorem, right? So if f is continuous on a closed interval, then max and min exist. But this direction is not going to hold in roll, right?
This is just the case where you just make sure you know what the conditions are and what the conclusion is, and make sure it goes from condition to conclusion, not the other way around.
Yeah, very good point.
I think only students who actually have the chance to do MATH1131, the discrete maths, will really get to dig into this very well. But for the rest, just conclusions and conditions are very different. Last question?
Yep, sounds good. So if I can't apply the max-min theorem, I don't know. There might be a max, there might be a min, there might be both, there might not. But if I can apply max-min, then I know for sure there's a max and a min. But I can only talk with that direction, yeah.
The word will sounds like there's a theorem lurking behind it, like you're saying you have to have something. That would be a theorem, and there's just saying there's no theorem to apply in this case. All right, final question, and it's another theorem. So we had a max-min theorem. Now we're going to look at the mean value theorem. Now I didn't copy in the responses because actually this is a theorem you should have committed to heart. So I don't even need to know what these boxes, what options they're offering up. I know what the option has to be before I even click on it. So you remember mean value theorem, it involves a closed interval and an open interval. They've already mentioned an open interval here. So it has to be something on this open interval. Whatever it is, it's going to be some synonym for differentiable. And probably it will just be the word differentiable. Now for the other one, just looking at what it says, it's f is something on something. Well, it told me about the open interval, so this better be the closed interval. And this better be the word, or some synonym for continuous, probably just the word continuous. Now, what the theorem says is, if you have this situation, then there is some point C in the open interval such that this average slope is going to equal to the slope at that point. Now, I guess this isn't a very good question for an open book exam because you could just open it up to the definition and read it off. I actually wouldn't really mind a question like that. I want people to really see this definition again and again and again, this theorem. So I'm not going to put it in this one, I'll say, but it would be a nice question in either case. Okay, so that's part A. Part B, we're given a particular function f. We're told that the mean value theorem guarantees on this closed interval that the instantaneous rate of change at some point f of alpha. So it's just really asking, saying, what does the mean value theorem say here? It says there exists some point in, there's going to exist some point in here such that it is equal to some average rate of change. I really just need to put in the average rate of change. It's f of 1 minus f of 0, 1 minus 0. That's actually just f of 0, 1 minus f of 0. I had noticed that too, actually. So someone's asking, it says here, the mean value theorem guarantees a point in a closed interval. That's true because A, let's say C, in the open interval does imply C is in the closed interval. So if I say, if C is between A and B, strictly between A and B, it is in this interval. In fact, I know it's in a smaller interval, but this is still true. So the arrow goes this direction. This implies this conclusion. As we just saw in the last one, this conclusion does not imply that condition. So this is not true. So all they've done here is they've been a little bit lazier in their conclusion. They could actually make a stronger conclusion than this. They could say it's actually between 0 and 1, not including 0 or 1. What they said isn't false. It's just not as accurate as they were given by the theorem. That is why I guess it is true. The theorem does guarantee this. It actually guarantees even more. At least it guarantees this. It also says that over the interval 1, 2, there is some beta. So there's going to be some beta where f of 2 minus f of 1 over 2 minus 1 is going to be beta, and that's actually just f of 2 minus f of 1 again. So it's the difference between those two numbers. Now, okay, the difference here, which I'm just realizing, is they have given me a particular function. So I think they are going to want the actual have I misread this question? Let me think about this again. I think I have misread this question. I have misread this question. No, I've misunderstood what the question was asking me, so this is a good thing to catch now. So let's reread the question. So it says we're trying to find a point which the mean value is, so let's find the point A such that the instantaneous rate of change at alpha, so I have that f of alpha is equal to the average rate of change. So what they're saying is we're trying to find alpha such that this is true. Okay, so I was answering the wrong question. I wasn't thinking about what the question was really asking me. Okay, so this does involve calculations. First things first, this would be 2 alpha minus 3 has to equal, and here's where a calculator would be very helpful, but these numbers aren't so bad. F of 1 is just 1 minus 3, which actually, I guess if I'm clever, which sometimes I am, not often, I only need to look at this. The average change I get from a constant is 0. So that means I really only need to look at what the values are here, which is 9 minus 9. No, sorry, brain was minus 2. So let's see, I get 1 minus 3 minus 3 minus 3 over 1, which is, so those cancel out. I get minus 2. So that means 2 alpha is equal to, it would have to be equal to 1. Just add 3 to everything. So alpha is a half. Okay. So sorry, it was a number. I was supposed to work out alpha is a half. This is the point where you get that average rate of change. Okay. What about beta? So the next part of the question, we're trying to find where f of beta is equal to f of 2 minus f of 1 over 2 minus 1, which thankfully is just f of 2 minus f of 1. So what is that going to be? That's going to be 4 minus 6 minus 3. 4 minus 6 minus 3 minus 1 minus 3 minus 3. As I saw before, actually this constant doesn't affect the average rate of change. I just get minus 2 plus 2. Is that right? That becomes a no. Where did I? 0, is that right? Okay, so apparently that's 0. Now that means 2 beta minus 3 equals 0. 2 beta is 3. Beta is 3 halves is 1.5. I probably won't use 1.5. I use 3 over 2. Use the exact fraction. So 3 over 2, and that is between 1 and 2. Okay. Now finally, it says, let's compute the sum of these two numbers. Now, I already calculated those because f of alpha is just actually equal to this number. And f of beta is just this number. So it's minus 2 plus 0, it is minus 2. Now here's where the question does take a bit of a left turn. I don't like the way this is worded, but it seems to introduce a new function. It says, now let's introduce a new function. It has the same name as our previous function. That's a little bit confusing, but it is a new function. Let it be a differentiable function where f of 0 is minus 3 and f of 2 is minus 3. Or is it the same as this function? Am I making a mistake? So 2, 4 minus 6, 4 minus 6 is minus 2 is minus 5. So it's not the same. So this is a new function. It's not the same as the function in the original question. Okay. Now it says apply the mean value theorem twice to the intervals 0, 1 and 1, 2. Then the numbers alpha, beta, for which alpha and beta satisfy the mean value theorem, are always such that this something. Now, that does seem confusing. So I really have to dig into this because this last question does seem a little bit odd. So what do we know? Well, the mean value theorem says these are going to give me f of, see, it's going to be f of 1 minus f of 0 over 1 minus 0 plus f of 2 minus f of 1 over 1 minus, 2 minus 1. Now, I can't do anything with this as it stands because I wasn't told anything about f of 1. But here's where the special situation actually, the specialness of this situation kicks in. This number is 1 and this number is 1. So this is really just f of 1 minus f of 0 plus f of 2 minus f of 1. So it's actually f of 2 minus f of 0. So that was just this combination here. So this should just be f of 2 minus f of 0, although here we're told we have values for that. So that is minus 3 minus 3? Yeah, that is equal to 0. So this should be 0. That's very curious. So let's get these answers in. Back to Maple, DA. All right, so this is supposed to be continuous. So let's just think about what the options were. So I think it's actually best to know the answer before you click on this box because you don't want to be confused by other answers. So I said it was supposed to be continuous. I mean, these are all nice adjectives, but only continuous is the one I want. And it's supposed to be the closed interval, so there. Yeah, closed interval. So continuous on its domain. I mean, that on its domain. All positive numbers. Yes. That's not part of the theorem. The theorem definitely just says all you care about is the closed interval. So this would not be the theorem as we've taught you. Let's see, it has to be differentiable on the open interval, and there's a point called C, such that the derivative at C is this, so it should be f prime C. Here it is. So yeah, I think it's probably best to know what you want to find on the list before you click on the list, because there's a lot of options here that look very similar. All right, so what do we get? We got that alpha was a half, 1 over 2. Beta was 3 over 2. And the sum of these two things was minus 2. And this one was surprisingly 0. Now, I'm curious to know if it would have accepted this answer, because this is sort of, in general, this is true. This is the sort of the answer for this question. No, so they didn't predict anyone would answer that, so it doesn't work. You have to do 0. Because I think I would have given half marks to that answer, because it kind of does ignore the question, but it does know what it's doing. Yeah, that's true. So yeah, just pick a nice, a nice function which matches these two. Sean, did you get the same numbers? Was it both -3 or?
No, sometimes they aren't the same value.
Okay, so I was
it's not
just
always
lucky.
right. Yeah.
Yeah, I was lucky. Oh well. Right, so that was the last question. There is one more question on the list, but it's the question that you're happy to see. It is the end of exam. So this is not a question. It's just there to tell you you've reached the end. If you have time, go back and look at your working. I wonder if I should tell them about that, because this was off record before. Tell them about those matrix entries. So there was a question, I think it was question 6. No, next one. So I was reading over the answers to this just to get an idea of what students were doing. And a lot of students were talking about the following matrix, something like the following. Make that larger. Something like that. Trying to do their explanation talking about this matrix. Now that's a bit of a problem, because if I go leave the question and come back, you'll notice that my answer has mostly vanished. This is just because this syntax I'm using, if you know anything about the way the web works, this looks a lot like an attribute tag. It looks a lot like HTML. So the computer has just completely eaten. All you need to do is make sure you put a space here, but it's kind of annoying to do that. So my suggestion is just try not to. If you want to be cautious, one thing you can do is type this up in a text editor outside of MapleTA and then copy it in. That way you at least have a record in case something goes wrong. It is nice to have backups. That's something I've learned using computers quite a lot, is it's nice to have backups. But that's all I really want to say about that.
Yeah, I would also say I think the equation editor this is another one of those rare cases where I don't mind using the equation editor because it has an option to enter a matrix really nicely, I think.
Yeah. Yeah, it is better. Anyway, so you can talk about the determinant of this. I think some students did do that, but you can give the explanation not using any of these sort of references to a matrix. Just talk about what happened in your calculation. All right, so we'll stop there. Any last questions before we finish the stream?
Yeah, no problem, everyone. Good luck with your exam.
Yeah, good luck with your exam. We're not having any more live tutorials like this. This was the last live thing for the year. If you ask any questions with enough lead up time on Moodle, you might get an answer.
Yeah, and don't forget the consultation updated timetable. There'll be multiple people available, 10 to 12 and 2 to 4 every weekday leading up to the exam.
Yeah, I had one yesterday and almost nobody turned up. So try to turn up to these things. Make use of the time provided. Right, well, good luck, and hope to maybe see you around in MATH1231.
Yeah, thanks everyone.